Hello everyone, welcome to this session. Today, we will explore the application of PLC control in vending machines. With the development of technology, vending machines have become increasingly common in our daily lives. They not only make our shopping experience more convenient but also vividly demonstrate industrial automation technology. In this lesson, we will learn how to use a PLC to implement various functions of a vending machine through a specific case study, S7-1200 PLC control of vending machines. In this task, the vending machine accepts 1 yuan, press S0, 5 yuan, press S1, and 10 yuan coins, press S2. When the total value of inserted coins equals or exceeds 12 yuan, the soda button indicator light L1 will turn on, indicating that soda can be purchased. When the total value of inserted coins equals or exceeds 15 yuan, both the soda and coffee indicator lights will turn on, indicating that both soda and coffee can be purchased. When the soda button indicator light is on, pressing the soda button will dispense soda for 7 seconds and then automatically stop. During the soda dispensing process, the soda outlet indicator light Y1 will flash. When the coffee button indicator light L0 is on, the process is the same. If the total value of inserted coins exceeds the amount required for the selected item, 12 yuan for soda, 15 yuan for coffee, the change indicator light L3 will turn on after the purchase. The change process will last for 7 seconds, after which the L3 light will turn off. Next, we will analyze how to implement this task. First, we need to count the number of each type of coin inserted, calculate the total value of each type of coin, and then sum these values to get the total amount of money inserted. Using comparison instructions, we will determine if the total amount of inserted coins meets the required amount for soda or coffee, and control the corresponding indicator lights accordingly. When the soda or coffee purchase indicator light is on, pressing the respective button will control the corresponding indicator light to flash. The flashing duration will be controlled by a timer instruction set to 7 seconds. Once the time is up, the flashing indicator light will turn off. Using subtraction instructions, we will determine if change is needed. If the difference between the inserted amount and the required amount is greater than 0, the change indicator light will turn on for 7 seconds, after which it will turn off, signaling the end of the purchase process. This task includes a knowledge points such as addition, subtraction, multiplication, division instructions, calculation instructions, trigonometric function instructions, increment and decrement instructions, maximum/minimum value setting limit instructions, and other function instructions. Mathematical operation instructions can perform basic operations such as addition, subtraction, multiplication, division, modulus, and absolute value for integers, long integers, and real numbers. They can also perform extended operations such as square, square root, natural logarithm, exponential operations based on e, and trigonometric functions for floating point numbers. Let's explain the ladder diagram format and application of each function operation instruction in detail. 1. Calculation instruction and addition, subtraction, multiplication and division instructions. The diagram above shows the ladder diagram representation of arithmetic and calculation instructions. The EN terminal is the enable input, IN1 and IN2 are the data inputs, out is the output for the operation result. And auto is used to set the data type. Calculation instructions are used to define custom mathematical expressions. Logical operators can also be used, with no constants allowed in the expressions. The input and output data types must be consistent. Calculation instructions are very convenient to use. They work like scientific calculators where you set the input variables and directly enter the calculation steps to get the result. The expression is displayed in the middle box. For example, S equals IN1 plus IN2 times IN3. If the input enable signal is 1, the compute instruction will be executed. The values of operands IN1 and IN2 are summed, and the result is multiplied by the value of operand IN3. The product is then transmitted to the out operand as the final result. If the instruction executes successfully, the ENO enable output and the signal state of the tag_output operand will be set to 1. The addition, subtraction, multiplication, and division instructions are ADD, SUB, MUL, and DIV, respectively. The data types of the operands they execute can be integers, sint, int, dint, usint, uint, udint, and floating point numbers, real. IN1 and IN2 can be constants. The data types of IN1, IN2, and out should be the same. The addition instruction adds the value of operand IN1 to the value of operand IN2 and outputs the result to operand out. If the sum of the values of IN1 and IN2 exceeds the maximum value for the data type, the output result will be 0. You can increase the number of operands in the addition instruction by using the asterisk symbol. The subtraction instruction subtracts the value of operand IN2 from the value of operand IN1, with IN1 being the minuend and IN2 being the subtrahend, and outputs the result to operand out. The multiplication instruction multiplies the values of operands IN1 and IN2 and outputs the result to operand out. If the product of the values of IN1 and IN2 exceeds the maximum value for the data type, the output result will be 0. You can also increase the number of input operands in the multiplication instruction to multiply 2 or more operands, with the result being output to out. The division instruction divides the value of operand IN1 by IN2 and outputs the result to operand out. For integer division, the quotient is truncated to an integer before being output as out. This example involves calculating the result of a digital output after inputting an analog quantity. The temperature sensor has a range of -100 to 300 degrees Celsius and an output signal of 0 to 20 milliamperes, where -100 corresponds to 0 milliamperes and 300 degrees Celsius corresponds to 20 milliamperes. After conversion, this corresponds to 0 to 27,648. Therefore, when the digital quantity is N, the converted temperature result is C equals N times 400 divided by 27648,100. In programming, first use the conversion instruction to change the data type of N to a real number, then use the division instruction to divide by 27648, obtaining the ratio of the digital quantity N in the range of 0 to 27648. Next, multiply by 400 and subtract 100 to get the temperature value. The specific programming is shown in the diagram. 2. Sine, cosine, tangent instructions. The diagram shows the ladder diagram expressions for the trigonometric functions sine, cosine, and tangent. The angles and trigonometric function instructions are all floating point numbers in radians. If the input value is a floating point number in degrees, multiply the angle value by 180 and then divide by 3.14 to convert it to radians before using the trigonometric function instruction. In the example, 3.14/180.0 is calculated first, followed by 45.0 times 3.14 divided by 180.0, converting 45 degrees to radians, then calculating the sin value of 45 degrees. 3. Increment and decrement instructions. 1. Increment instruction, diagram A, shows the ladder diagram format of the increment instruction. If the enable EN signal state is 1, the value of the operand IN/out is increased by 1 and outputted to IN and out. 2. Decrement instruction, diagram B, shows the ladder diagram format of the decrement instruction. If the enable EN signal state is 1, the value of the operand IN and out is decreased by 1 and outputted to IN and out. 4. Maximum, minimum, and limit setting instructions. Diagram A shows the ladder diagram format of the maximum value instruction. Diagram B shows the ladder diagram format of the minimum value instruction. Diagram C shows the ladder diagram format of the limit setting instruction. For the maximum and minimum value instructions, the EN terminal is the enable terminal, which must be 1 for the instruction to execute. IN1, IN2, and IN3 are input terminals, and OUT is the data output terminal. For the limit setting instruction, the EN terminal is the enable terminal, MN is the minimum value terminal, IN is the data input terminal, MX is the maximum value terminal, and OUT is the output data terminal. Next, we will explain the application of the maximum, minimum, and limit setting instructions. The maximum value instruction, MAX, compares several input values to determine the largest value and outputs it to OUT. You can expand the number of inputs for this instruction, requiring at least 2 inputs and a maximum of 100 inputs, numbered in ascending order in the function block. In the MAX instruction module shown in Figure 426, among the values 67, 226, and 3201, the maximum value is 3201, so OUT equals 3201. The MIN instruction is used to compare several input values and output the smallest value to OUT. The MAX instruction, in contrast, numbers input values in the function block in descending order. In the MIN instruction module shown in Figure 426, among the values 13, 16, and 58, the minimum value is 13, so OUT equals 13. The limit setting instruction, limit, restricts the input IN value to within the range MN, MX. If IN satisfies the condition MN less than or equal to IN less than or equal to MX, its value is copied to OUT. If IN does not meet this condition and is below the lower limit MN, the output is set to MN. If it exceeds the upper limit MX, the output OUT is set to MX. In the limit instruction module shown in Figure 426, the input IN is required to be within the range 15.0, 95.0. Since the input is 100.0, which exceeds the upper limit, the output OUT is set to 95.0, the upper limit value. This concludes today's lesson. We will continue in the next lesson.